Welcome to today's Explainer. Today, we're going to take some pretty complex optical physics and translate it into a crystal clear understanding of the beautiful, everyday phenomena that completely surround us. Now, notice how ocean waves don't just, travel in a perfectly straight line. When they crash and pass through a narrow gap in rocks, they gracefully fan out. They bend. It's this mesmerizing ripple effect that feels so entirely natural, yet, believe it or not, it's governed by some incredibly strict mathematical rules. Or how about this? Have you ever actually wondered how a simple plastic compact disc magically conjures up a brilliant rainbow literally out of thin air? We've all seen that familiar, super colorful reflection on the back of a CD, but what's actually happening to the light when it hits that surface? Well, let's dive right into this, because the exact same physical principle that explains those ocean waves and that CD rainbow, it also explains why you can hear someone speaking in the next room without actually seeing them. Sound waves, water waves, light waves, they are all playing by the exact same hidden rulebook. So here's our roadmap for this explainer. We'll start with an introduction to optics, then define diffraction, explain Huygens' principle, look at the single-slit experiment, compare interference versus diffraction, and finish up with some real-world applications. Let's kick things off with Part 1, Introduction to Optics, entering Dr. Brar's UPH 013 course. Moving on to Part 2, Bending Waves, Defining Diffraction, the secret of spreading waves. So the actual mechanism behind the mysteries we just mentioned is called diffraction. It's simply the bending or the spreading out of waves as they pass by objects or through a finite width aperture. But here is the absolutely critical part. This bending effect is highly dependent on the wavelength. And that perfectly explains why sound waves, which have relatively long wavelengths, easily diffract around doors and corners. Visible light waves, on the other hand, are microscopically small, so they generally seem to travel in straight lines, unless, of course, they hit a tiny enough obstacle. Part 3. Huygens' Principle Explained. Unobstructed Points as New Wave Sources. To understand exactly how a wave bends like this, we've got to zoom way in to the microscopic behavior of the wave itself. Just picture every single point on a water wave acting like a brand new pebble dropped into a pond. According to Huygens' principle, each of these unobstructed points creates secondary ripples, and all those tiny new ripples combine to form the new overall wave. It's literally an infinite forward-moving chain reaction of wave creation. Which brings us to Part 4, the single-slit experiment, squeezing light through a tiny gap. Now, let's see what happens when we force light through an incredibly narrow opening, where the width of the slit is right around the actual wavelength of the light itself. Because of those secondary ripples we just talked about, instead of a single, boring, straight beam of light on the wall, the overlapping waves create a brilliant, intense central peak. And flanking it, you get these fading, symmetrical bands of light and dark. The wave is literally interacting with itself to create this pattern. But the math reveals something totally surprising about this. The light doesn't just gently fade out like a gradient. Actually, its intensity absolutely plummets. The very first secondary bright spot right next to the middle is profoundly dimmer. It's only 1/22nd as bright as the center, and it continues dropping drastically at every step from there. So after dropping to 1/22nd, the next band gets 61 times dimmer than the center, and then a staggering 121 times dimmer. It's like a rapid mathematical cliff of light intensity perfectly laid out by the wave. Part 5. Interference versus diffraction, the great optics showdown. Now, to clear up probably the absolute biggest point of confusion in optics, we really need to separate diffraction from interference. See, while interference requires two completely separate coherent sources, meaning waves that are perfectly in sync, kind of battling it out to create perfectly dark spots, diffraction is fundamentally different. Diffraction is a single wave interacting with itself, originating from secondary wavelets on the exact same wavefront. And that is exactly why the fraction minima aren't perfectly dark and why the maxima have those rapidly fading intensity patterns we were just looking at. As we scale up the complexity here, going from a single slit to a double slit and finally to a massive diffraction grating with tons of slits, it's fascinating to watch how the math evolves. The governing mathematical parameters, mainly alpha and beta, actually shift to dictate the entirely new patterns we observe. Part 6. Real-world applications. From mathematical theory to powerful technology. All right, let's zoom back out to the macro world for a second, because this bending of light, It's the literal engine behind some massive technological breakthroughs. For instance, understanding how diffraction rings spread outwards dictates the absolute limit of resolving power in optical instruments, meaning it defines exactly how sharp an image a telescope can possibly capture of a distant star, or exactly how deeply a microscope can peer into a tiny cell before the image just blurs out completely. Honestly, the applications are endless, from determining the atomic structure of crystals using X-ray crystallography, to embedding those little 3D holograms on your credit cards, to reading data off those CDs we mentioned earlier. Mastering diffraction is a total game changer. It's the key to measuring material stress in manufacturing, and it even powers the fiber optic laser technology used in modern communications. We've basically built the modern scientific age by understanding how to bend light. Which leaves us with this final thought. As we continue to manipulate the very shape and direction of waves with ever-increasing precision, what completely new technologies will we unlock once we fully master the infinite ways to bend light? What everyday mysteries will we turn into tomorrow's cutting-edge innovations? Just keep that in mind the next time you hear a sound coming from around the corner. Thank you so much for joining me for this explainer.